So welcome back to another video, and in this one, or lesson 4, we're going to be looking at quantum uncertainty through waves and particles. So starting out, let's go over some of our elementary knowledge. So when we think of an atom, we may think of Bohr's model. So Bohr's model, proposed by Niels Bohr, basically describes the atom as being this charged nucleus with all of these rings around it, and within these rings we have all of these little negative subatomic particles called electrons. And then inside the nucleus we will have protons and we will have neutrons making up the mass. And then as an atom gets bigger and bigger and goes further out on the periodic table, they will have more shells with more electrons and more electrons. But naturally, through hypothesis comes further alterations and specific limitations. So just going over some limitations to Bohr's model, because although it laid the groundwork for a lot of modern chemistry, it does have its limitations, and specifically, it does not explain how energy levels are stable. So first we have the stability of, I'm just going to write E for energy levels. That's one, and then the second point that we have is it's not as accurate, or it's not that good of a predictive model for any element other than hydrogen. So what we're really saying with this last point, and why it's not as accurate as a predictive model for most elements other than hydrogen, is because when we look at hydrogen, hydrogen is just our nucleus, right? We have one proton inside, and then inside the first ring, we have an electron, right? Simple, hydrogen, that's our Bohr model. But when we look at more complex ones, or more complex atoms that have more than one electron, right? Let's say we have oxygen, and oxygen has 6 valence electrons. So we can go 1, we can go 2, 3, 4, 5, 6, right? The Bohr's model doesn't really work that well here because it doesn't explain the electron-electron repulsion, basically why the electrons are keeping away from each other. And also, Bohr's model doesn't describe why electrons are in fixed orbits around the nucleus. So now we're moving into what we like to call the uncertainty principle to solve these limitations. So the uncertainty principle basically states that certain pairs of properties cannot have exact values, but it also states that position and momentum are of these pairs. So what this is basically just saying is like where something is, or the movement of something, where it's going, right? Like its momentum, are uncertain with each other, right? They're the property pairs. From this comes a specific relationship between uncertainty and precision, right? Because these are our property pairs. So we can say if uncertainty, so the uncertainty of an event, if that goes down, then the precision of such an event will go up because they're in pairs, right? One goes down, one goes up, the property pairs. So the uncertainty principle is a mathematical relationship developed by Werner Heisenberg, which states that delta x, or the uncertainty in the position, multiplied by delta p, which is the uncertainty in momentum, which from physics is mass times velocity, is greater than or equal to Planck's constant, which is negative 6.626 times 10 to the negative 34 over top of 4 pi. Now you're probably wondering, what does this equation mean? Well, it's basically saying that the more precisely you know where a particle is, the less precisely you can know its momentum. And this isn't due to a measurement error. It's basically just a built of just the nature at quantum levels and on things at a subatomic scale. So you might be wondering, why is all this important? Well, basically, all this matters because it just shows that unlike the planets in our solar system, where we have the sun, then we have orbit, and we'll have Mercury, further out, more planets, all orbiting around the sun as these individual balls of mass. Instead of that, we have these subatomic areas of high certainty or high certainties or probabilities of where an electron should be versus areas of where an electron should not be. So it's all hypothetical about where an electron actually is in its position and momentum in spacetime. So now we're going to be getting into what waves are specifically. So this may be a review for many of you who have taken grade 11 physics before or who have already done grade 12 physics. But basically, when we look at waves, we think of standing waves. So standing waves were mainly proposed by Schrodinger and also Louis de Broglie. So to them, an electron bound to the nucleus in an atom resembled a standing wave. So this is why it's important that we talk about it. So we use the sign of lambda, which is kind of like this upside down y, to represent how many wavelengths we're looking at. So let's just look at one wavelength. So we'll go from here to here. And then what we have is we have an upwards to a crest, back down to the wave, and then downwards to a trough, and then back here. So we started at this position and we ended at this position. So the wavelength is 1. It's almost when you think of like the sine curve, right? This would be 1 period, 2 periods, and then half a period, right? Or you could think of cosine. So you see waves all over the place when you look at different STEM courses. And then if this is 1 lambda or 1 wavelength, then what would 1/2 be? Well, it's simple. We just go from here to here. So it's just the trough. So we start from 0 being the height, and we just go to, let's say this is 1 as our maximum. Let's say we have -1, right? Let's look at like a sine curve. We go up to 1, down to 0, -1, back to 0. But here, we just go up to 1, back to 0. So it's really just half of what we had before. Now, if we have 3 over 2, right, that's synonymous to 1.5. So if we start here at 0, right, like we did for the other ones, we can go up to the crest, to the 0, down to the trough, back to 0, and this is 1. But we still have 1 over 2. So we can take our second example and just add it here. And just like that, we have 0 to the crest, to 0 to the trough, from 0 to the crest, to 0. We have 1 wavelength plus this, which was our 1/2 wavelength, to make 2 over 2 plus 1 over 2, or 3 over 2. Now, I just want to kind of define some of these terms that you'll see pop up. So a node is basically a spot where there's 0 lateral displacement. And an antinode is pretty much just the crest of the wave. So I'm just going to pinpoint. So we'll use a pink for an antinode, and then we'll use a blue for our nodes. So on this graph here, we can have our nodes. So it's 0 lateral displacement, so there's going to be a node right here, and right here. On y equals 1, or sorry, lambda equals 1/2, we can go here and here, and then on 3 over 2 wavelengths, here, 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 here. So what you'll notice with the trend is that every time we add half of a wavelength, we're adding 1 node. Because here, or I guess you could say we had 1, technically, because we have no wave, we have no wave going up or down. But then when we had 1/2, then we have 2, then when we add 1/2 of that, then we now have 3. Add another half of that to 3 over 2, now we have 4. So it goes from n, and this is n plus 1, and this is n plus 1 plus 1, right? So it's a reoccurring trend. And now for the antinodes, so the antinodes are the crests of the waves. So we can have antinode here, right? Antinode here, antinode here. But I should have mentioned that when we look at antinodes, though, it's not only the crest of the waves. It's also, as I said, the troughs of the waves. So almost like the maximum versus the minimum. So where we have an antinode here, right, there would also be an antinode right down here, right? It's at the lowest point that it's at. So in this case, let's go back to our sine analogy. We have 1, 0, -1. There would be a node at 0, antinode at 1, antinode at -1. And then on this graph here, we wouldn't have another trough, so we would just go on 3 over 2, and boom, put 1 right there. So I just have a little demonstration here. So what we have here is these kind of figures illustrate the hydrogen electron represented as a standing wave around this nucleus, which we have in blue. So as you remember before, we just had our waves as being this straight line, and then we'd have a wave going like this around the line. But if we were to take this line and then perhaps transform it into being a circle, then this wave that we had on a straight line would still follow the same straight line, but just it would have a curved axis rather than a curved path. So what we're looking at here is basically on each of these waves, there is an individual, let's say, electron, right? Orbiting around hydrogen, because hydrogen has one electron, so we can see it going like all the way around here, right? Just orbiting like a planet orbits around the sun. So in the middle here, we have this circumference of each particular circular orbit, right? And it's getting bigger over time, right? We have 4, 5 is going to be the biggest, and then 4/3 is in the middle between them. So what this diagram basically shows is that the circumference of a particular circular orbit, those Bohr's, we have n equals 1, 2, 3, as we go further down the periodic table, it corresponds to a whole number of wavelengths, right? So let's say we have oxygen. So we have oxygen, and then we have 1 shell and 2 shells, and then 3 shells, right? We have like 2 here, 8 here, and then 6 on the third one. So then our n would be 3. Basically, this demonstrates that the electron doesn't have to move in a specific circular orbit around an atom, or sorry, a nucleus, but instead it can move on this orbital path going in the form of a wave. And the wave will perform constructive or destructive interference when n is not a whole number, right? Or it's not a natural number, right? So we could have n is typically elements of the natural numbers, right? But when we have this, it's almost like we have 2 waves, right, that are interacting. If we have 2 waves like this interacting, our resultant will be like this, and that's called constructive interference. But if we have a wave like this and a wave like this, starting from the same positions, then our resultant will just be a line. They will destructively interfere, and we will have no wave. Now, although this is a pretty good model that's different than Bohr's, it does have the one same misconception with Bohr's model, which is that electrons specifically orbit in a circular path around. So yeah, this kind of view just really emphasized Schrodinger's wave equation from before, and just the idea that it's impossible to know the exact position and speed of an electron at any given time.